Welcome to the talk on lyrics recognition and syllable assignment of medieval manuscripts. My name is Christoph Wick, and I'm glad to present our work in this digital format. First, I want you to give a short outline of this presentation. I want to give you the wider context of this talk and the paper, therefore how lyrics recognition and syllable assignment is embedded in another project. And then I want to present the different tasks that are covered in this paper. First, I want to talk then about the lyrics recognition, how we did this, and then how to assign individual syllables to the respective notes. Then I want to present the datasets we use to evaluate our methods and to discuss the results. Our goal at the University of Würzburg is to digitize and encode historical music manuscripts from the medieval age in so-called Gothic or square notations, which are Neume notations. On the right-hand side, you see two example pages, one in Gothic and one in square notation. You see that there are staff lines and there are notes, which are called neumes in the context of medieval music. Our goal is to capture both the melody and the lyrics. Therefore, we first have to detect staff lines and clefs and notes, but we also have to recognize the text. And the text, this is what this paper is about. But if we have the lyrics, we also need to know when a specific syllable is sung. So we need to know about the connections between a syllable and the note to obtain the full digitization of the manuscript. Furthermore, on some pages, there's also additional text present, for example, the red text at the bottom of the example page in Gothic notation. We call this paratext, and we will not cover the recognition of paratext in this talk. We only cover lyrics recognition. This slide shows an example music line transcription as we perform it in our project. The upper image shows the original manuscript, which is an extract from the complete page, and the lower figure shows the transcription equivalent. So you see we use common Western music notation to represent the music, and that we separate syllables by hyphenation with a dash, and each syllable is centered below the first respective note of a neume. And it is possible that there are several neumes per syllable, but it's not possible that there are several syllables per note. After having you presented a brief example of the complete transcription, I can introduce the tasks of lyrics recognition and syllable assignment itself. The input for the automatical transcription of lyrics is the image of a single text line image. The bounding boxes of this text line are already present in the ground truth, therefore we do not have to cover the line extraction. However, as I will show later, there are two different types of lyrics extraction. One is automatically extracted and the other one has been manually corrected, therefore the complete characters are included. The output of this task is, of course, the transcription. The transcription can either be diplomatic or editorial. I want to explain later what the differences are. To evaluate the task, we use the character error rate. The second task is the assignment of syllable to neumes. The input here is the already present editorial transcriptions, therefore a human has corrected the errors in the automatic transcription. And we also have the transcription with is split into syllables. Therefore, we have perfect inputs, so to say. Furthermore, we can use the single text line image, the same from the automatical transcription of the lyrics. And, of course, the position of all neumes. The output is a list of connections to the syllables, which is shown in the orange arrows. To evaluate the assignment, we use an F1 score, which measures whether a connection is present or not. As I already said, there are two types of lyrics line extraction. The image on the left-hand side shows the automatic extraction, which is basically the space between two staves, and the staff lines are already detected in the ground truth data, so we just use the space between two staves and extract this as lyrics region. This may result in lines, which you see at the bottom, that are cropped. Furthermore, we use an accurate extraction, which is corrected manually, and therefore there are no letters cropped or cut and missing. On the bottom, you see, again for comparison, two example lines and the transcription. Furthermore, in the dataset I will present later, there are two different transcription alternatives. Some data use a diplomatic transcription where abbreviations are also in the transcription, and there's also an editorial transcription where abbreviations are resolved. This might lead to severe changes in the text. For example, the sancta are 3 letters in the image line, but 6 letters in the transcription. Furthermore, there might be some editorial changes, for example, the change of S and the long S, which are not consistent across all words. To solve the text recognition, we use the automatic text recognition engine Calamari, which is an ATR engine optimized for small datasets, but mainly for printed documents. The default network architecture consists of 2 CNN and pooling layers, followed by a bidirectional LSTM and a fully connected layer to obtain the logits. The model is trained with the segmentation-free CTC loss, and the code is open source. It's available on GitHub. The syllable assignment algorithm is a bit more complex to present, but it's rather simple. We use as accessible input the staff with the text line, so also the text line image, and the known lyrics. Then we apply the automatic text recognition on the image line again to obtain the text, which might contain errors, but also the positions of the characters. After aligning the prediction and the correct lyrics, which were manually corrected, we can obtain positional information for each character to the corrected text. As a result, we have characters and the position of each character. Then we can divide the characters into syllables based on the known lyrics. And then we can use the mean value of all positions of the characters within a syllable to find the closest neum. However, it might occur that with the simple algorithm, 2 syllables are assigned to 1 neum, which must not occur. Therefore, if we have a neum that is assigned to 2 syllables, we move one connection to the left or to the right to see how we can resolve this conflict. The resolution is shown with the dashed green arrow. Now I want to introduce the different datasets. We had access to 5 different datasets. However, not every dataset could be used for both tasks. The Salzinnes and St. Gallen datasets could be used for the ATR only. However, they contain a diplomatic transcription. These 2 datasets were kindly provided by the McGill University in Montreal, Canada. The other 3 datasets are Assisi, New York, and PA 15819. All 3 datasets will be made available on GitHub. These datasets contain the complete transcription of staff lines and symbols, but also syllables. However, use an editorial transcription. Furthermore, the line segmentation was performed automatically and only on 15819 manually. Therefore, we can use Assisi, New York, and PA 15819 to evaluate the syllable assignment and the editorial transcription However, Salzinnes and St. Gallen only to evaluate the diplomatic transcription. Moreover, PA 15819 can only be used to compare the accurate and automatic line segmentation because this is a dataset where both methods are present. Also note that Assisi and New York only contain about 50 lines ground truth. Therefore, we expect that the results of the automatic text recognitions are very poor. After having presented the dataset and the methods, I want to show you our results of the ATR, which is the character accuracy on the books. The table shows the books, the number of training lines that were available, and the results. We performed 2 experiments. In the first one, we used the training data of the book itself to obtain the character accuracy, which is same. In a second experiment, we want to evaluate how good a model trained on other books works on one specific book, which is denoted by the cross values, which are obviously worse than training on the book itself. The first thing to observe is that the number of training lines have a high impact on the character accuracy. For example, on PA 15819, where we have the most number of training lines, we also get the best result with about 6.7% character error rate. On the contrary, on Assisi, where we have only 40 lines of training data, we get about 30%. The results of the cross-book training shows that it is not possible to train a general model at the current early stage, because even on New York, where we have the most number of training lines, when we combine all other 4 datasets together, we obtain a character error rate of about 25%, which is rather high. Furthermore, we compared our proposed method to the results of Duruus, who kindly provided the data for Salzinnes and St. Gallen. They used Occupy as their ATR engine, and one sees that Calamari yields improved results. As expected, the most common errors are missing letters such as I's or white space, or confusions of S and long S, C on T, NMN, and so on. On the next slide, we compare the accurate and the automatic line extraction by also varying the number of training lines. As expected, the accurately cut out lines yield a lower character error rate, and about twice the number of automatically extracted lines were required to obtain similar results. However, the automatic approach might be sufficient if the goal is to search the lyrics in a large collection of ecclesial texts, if available, or to obtain a large number of training examples. This slide shows the evaluation of the syllable assignment. The baseline is that we assign each syllable one by one to each neum in order. This means, of course, if the first assignment is wrong, all subsequent assignments are also wrong. However, this approach already yields an F1 score of about 87%. We compare the baseline to RTR models that were trained on a different number of training examples that yield, therefore, a different quality of the position information. Ntrain equals 0 is the default Calamari model, which yields a character error rate of about 42%. However, it increases the baseline by about 3%. A model with a character error rate of about 10% is already sufficient to obtain an F1 score of over 99%. A higher character error rate does not improve the F1 score further, which shows that these are either ground truth errors or fundamental shortcomings of the algorithm itself. For example, by enforcing that all syllables are linked to a neum, which is not always the case. Finally, I want to give you an outlook how we want to improve the algorithms. First, we want to incorporate a dictionary for text decoding. The problem, of course, is the hyphenation at the end of the line, which might break words into 2 lines. Next, we want to build up a corpus of medieval ecclesial texts, which is meaningful because often the same text is set to the music in different versions. And then we want to search for this text based on poor RTR results to obtain the correct text and therefore the correct lyrics. Furthermore, we want to improve the syllable assignment algorithm by implementing and testing more sophisticated alignment methods, such as dynamic time warping. Finally, we want also to improve the new recognition by detecting areas where syllables were found but no notes. This might help to find missing notes. Finally, I want to share some links. The parent project OMMR for All includes the code for lyrics recognition and syllable assignment and the evaluation, and also a link to Calamari, which we used for automatic text recognition. Thank you for listening.